All right, it is 10:30, so we will get started. Let people filter in. If you have your homework, you can just hand it in after class. Some people have it in already, I see, but well, you can. I mean, it doesn't matter. You can at the end of the class. I guess people that are coming in late won't hear me say that though, so they'll just probably come up and bring it. So, oh well. All right, so a few administrative things. The first. Actually, you know what? I'm going to wait till the end of the class to talk about this. This is about the homework, the next homework. Given this last homework, I had a few changes. I wanted to make a few changes on it and basically write out things a little more explicitly. I think maybe too much was left kind of implicit in the last homework. So I'm going to take a little bit more time and edit that to be, it'll be very long, the assignment, but really hopefully it sort of works you through all the different steps. I'll repeat this all when everyone at the end of class though, so everyone can hear it. But that will be out either probably today or tomorrow, maybe Saturday, depending on how travel goes tomorrow. But be out soon, and I'll send an email out to everyone when that's out. I think that's all. Were there any questions about administrative stuff, like the homework or the new problem set or anything? Any questions about that? Yeah.
Will we get feedback from the milestone?
I'll try to give that out probably over the weekend. I'll go through that all. The milestone, I mean, if you have questions, also come to office hours to ask about that. I'll look over them, but I'm not going to give very detailed feedback. So if you have a particular question, do just come and ask me about it in particular. Don't just assume that everything's fine because of the milestone. It's mainly just to get you kind of moving along. So certainly come ask questions if you have questions. Today we're going to keep talking about control. And in particular, we'll finish up talking about PID control, and we'll talk then about an example of this. PID control, the way I set it up is sort of when you have one variable you want to control, like in this case theta, you want to make it some reference value. I sort of motivated PID control in that regard. It turns out that the PID control is actually quite applicable in a lot of cases, even when there are dependencies between different variables in a big system. If you have certain types of control at your disposal, like control inputs at your disposal, PID control can still be quite good in a lot of cases. And so I'll highlight about why maybe PID control you would think shouldn't work for a certain case, but that it does work quite well. But then I'll talk about a little more general method. The issue with PID control is that we formulated it more as just kind of a system that takes some gains and achieves some desired set point for the system without really talking about this framework of optimal control that we talked about before, right? Where we talked about having a cost function and that you want to minimize this cost function over a long period of time. Our discussion of PID control thus far has been kind of absent in that discussion. So I'll talk next about linear quadratic control. And this is a type of control. It's actually quite similar in some ways to PID control, but it makes very explicit the connection between types of control laws like you get from PID control and an actual optimal control objective. So actually, if we define a cost function that we want to optimize over time, what sort of control laws does that lead to? And it ends up leading to a form that's actually not that dissimilar from PID control, but you can just also have correlations and connections between different variables. That's what we'll talk about there. We won't go into too much detail here. The math for linear quadratic methods, it's not that hard. It's just linear algebra, but it is kind of hairy. So I'll skip over some of the nastier math. If you're curious, I'm happy to sort of describe it, but I'll try to describe it from a high level, and the details you can maybe look up somewhere or figure out, and if you are indeed curious. So when we finished last time, we were getting to two of these three things for PID control, right? We were doing PD control. And the basic idea was we have some control input, UT, which is essentially the mechanical power we can put into our system. And we said this is going to be, we're going to set this equal to the electric power. And that's what's known as a feed-forward term. It means that if there were no errors, as we saw in that first slide, if you were at your desired point and you were at your desired frequency, then just this thing here would work. That's what you should sort of give when there's no error, right? But then when there is some error, when either your derivative terms or your theta angle, voltage angle here, are not at the desired amount, you want to have some additional inputs that will correct for this, right? And so we added, first of all, a P gain, which was proportional to the desired value minus the actual value. I'll write this, I guess it's theta at time t. And then the problem with that was for some systems that would cause a lot of oscillation, right? Because you're just looking at the thing you're trying to control. It's a system with momentum in it. And so you start speeding things up, but then by the time you hit your desired point, you sort of sped up the rotational velocity too much. And so you just oscillate back and forth like this, like you saw in this slide here. So what we did instead then was we also added this damping term, this KD gain, which was proportional in the general case to the desired velocity at time t minus the velocity at time t. Though oftentimes this term is just 0 because you just want to keep the system at a fixed point. So this term will be 0, and so the whole thing acts as kind of like a drag term on the whole system. It kind of slows down the dynamics by adding our own artificial forces. Not artificial, but our own intentional forces. So that's where we were at so far. And from this plot here, you can see this works pretty well, right? It seems like we start kind of far off, and we maybe overshoot a little bit, but then we settle back to it pretty quickly. Similarly, if this here, the blue line here shows the error in the theta variable, so how far we are from our desired voltage angle, which is 0 in this case. And then the red dotted line shows the actual rotational velocity of the generator minus the desired rotational velocity. And these two graphs here show two different sets of gains. And so this one you can see is looking pretty good, right? We are definitely converging to this. In fact, we get the right value in the end. But you might say, well, it's kind of still overshooting a little bit. It's not quite doing what we want to do. Maybe we could do a little better. And the intuition would be then that if it is oscillating some, well, it oscillates a lot when there's no D gain at all. So if it's oscillating too much, maybe you just increase the D gain a little bit, the KD gain. And so this one, you increase it from 20 to 50. Now you have a system that just very nicely settles into its desired amount. And by the way, this would happen from any initial conditions too. I'm starting at some initial condition. But so showing why in general will do from anything is kind of tricky here. And remember, for very far away points, starting points, you might start adding a whole lot of additional control input, which isn't very realistic. But for any point kind of around here, this would just nicely converge to this desired location. Yeah?
What would happen if you increase the KD more and more?
It would be like adding more and more friction to the system, right? So it would essentially slow down convergence even more. And at a certain point, it says, well, why really bother with that, right? Because you're already not oscillating too much. And so you really want to make it like a real sludgy, kind of slow-moving system. It would just take a lot longer to converge, right? It would sort of go like this. Just like you're adding more resistance to the system, resistance to change. Another way of thinking about this D gain is that it is a resistance to change, because you will apply, again, assuming the system is 0, you will apply the input of K negative KD theta dot t. So the faster your system's moving, the more force you apply, right? And you apply force proportional to how much it's moving. So if you turn this really high up, it means you'll start opposing any movement very quickly. Turn it up too high, and your system, in the ideal case, is fine. When you're this is a really differential equation, and you can change your control input arbitrarily fast. In the case where this is actually discrete, then what might happen is you set a very high control input, right? And the system slows down, but it slows down too much before you can even change your control input, and so you actually end up causing more oscillation from too high gains. In the ideal case, that won't happen because everything's differential equations and you'll sort of instantaneously respond to whatever your true velocity really is. But in the practical case, too high gains of any kind can actually cause oscillation. Don't worry about that if that was a little bit vague what I meant there, but you can get, you don't want to turn these too high, both, and also because you just start commanding really high control inputs, right? And that isn't a very good thing. You probably don't want to, put in arbitrarily large amounts of power into your system, or ask it to produce arbitrary. You can't do that in practice. And actually, we'll get to that later on as sort of what's wrong with a lot of these methods is they do just prescribe whatever control input you need for that situation, whether or not the system can actually generate that much, right? So a lot of times you can't actually generate the amount of power this would prescribe, so what do you do then? And then you want to get back to these optimization techniques. But we'll get to that, not this class, next one or the next one after that. Okay, the question now though is, so PD control seems to work. What's this last I term and why do we need that? And the problem is that in all these slides here, I've been assuming that we actually know what this thing is, right? I've been assuming we know how much power to put into the system to keep it at the state that we want it to be at. Right? If we didn't know what P elect was, electric power, then this is trickier, right? Because now, well, how much do we put in when we're at our operating point, right? And so what if we have some error in sort of our guess on this? What will happen then? And as you might expect, let's just drop this term out entirely and see what happens. And as you might expect, we're not ever going to actually reach the desired state, right? Because to reach the desired state, we want to have zero error here, right? So we have zero error here, zero error in the velocity. But the problem, of course, is that if you have zero error in both these terms, this would say apply no power to it. And so that would immediately knock you back out of that state because in order to maintain that desired state, you have to keep putting that right amount of power in. And so what happens instead is what you get. But it does work okay also, right? Because you do still have this notion where if you are far away from your desired point, you will still put in some power. And if you're far away from your desired velocity, you'll still put in some corresponding power. But you just never quite get there. And so what it looks like is this. You converge, and I guess this line here would be the 0. And so here we actually are converging to that. So we get the right speed. You have to because theta isn't changing. And if theta is not the right thing, then it'll change. That's sort of actually, I guess I should say, you don't have to do that, but is an effect of this particular system that you will, in fact, get to the right velocity. But you'll never get to the right theta angle. Yeah?
P elect is the power you generate from this generator.
P elect, so the U is the mechanical power you put into the system, and P elect is the electric power. And in general, these things have to be in balance, right? If they're not in balance, then the system will start slowing down. And these are the equations of motion for the systems. The system was theta dot equals omega minus omega ref, and omega dot equals 1 over 2h times, times the input, which is the mechanical power, U minus P electric. In general, this will come from the grid itself, like the power flow equations of the whole grid. Here, I'm just assuming one. Let's just say it's fixed. So we're just controlling one generator in some fixed way. In general, this will become from a set of those differential algebraic equations that make things more complex. So I'll actually get back to that in a second.
In which cases you don't know this P elect?
Oh, so if you just have I mean, you wouldn't, in the sort of general, so just think about controlling one generator. Everyone else is going to kind of do what they do, but you don't know what the load of the system is. You wouldn't know and how much everyone else is generating. You wouldn't know then how much power you should generate to keep the thing at the desired angle. There's no way to sort of know that ahead of time. So what do we do then? And this is where that integral term comes in the PID. So the idea is we're going to have another term that looks at this error that we have and integrates that error over time. So if we have some error in our steady state operation, it'll keep adding a little bit more and more force, or sort of more and more input here, until maybe we do settle to our system. And what this looks like is another term, ki times, well, we're going to take the sum of all the times from the start to right now. So the sum of all, I'll use tau to go from 1 to t. Remember, I'm prescribing an input at time t. I'm going to look at what the error was for all those times. D tau minus theta tau. We're going to add them all up and apply a force relative to that. Now in practice, you probably wouldn't want to keep your entire history of past states, right? Just to, recommit the sum every time. So what you do in practice is you keep another variable, which I'll call ET. And we'll maybe say E0 equals 0. And then ET, we update it as ET equals error at time t minus 1 plus the error at time t. This is just sort of an aside. This is the actual equation here, but I'm just saying to compute it in practice, you would just keep a running sum of what your errors are, right? And then you would multiply ki by this running sum. Does this make sense to everyone what we're doing here? Right, because what's going to happen here is that there's an error at all these times, right? Theta is not equal to theta d, its desired value. So every time it's not equal to that, we're going to be increasing the sum a little bit, right? This will be positive. And so every time we see this error, we add a little bit more to this term. We add a little bit more force in, power in. And if we're lucky, over time, what will happen is this will actually end up, despite the fact we have zero initial knowledge of it, this will end up actually equaling that feed-forward power we would want to put in. Just by the fact that this will only stop increasing or decreasing if we're actually equal here. If at time t, things are equal. And it'll be a fixed value. And so what happens is things work. What we get, so this is the full form of it now. We have this integral term here. And in our case, theta d is just equal to 0. So we're just subtracting the sum of all our past angles. And what happens is, as you would hope, we do in fact converge. This is without any knowledge of what that p elect is. We converge to the desired state in both of our variables. Now something's a little bit weird here, right? Because you sort of have, there's sort of two phases to this thing, right? There's the first phase where you're kind of at your initial conditions anyway. You're just kind of far away from where you want to be anyway. And so, well, what the error here is kind of meaningless in some sense. I mean, it's a lot bigger than the error here, maybe. Yet we're still adding up this sum of errors into our amount too. Right, so PID control with the I term can be very, very finicky for this reason. You can have things where you build up a very big integral term here, and that actually causes you to overshoot your goal, and then it takes a while to converge back to it. I sort of picked games here where this doesn't happen, so things kind of work out nicely here. But nasty things can happen here. You can imagine also if you just, for physical reasons, can't quite achieve your desired position, this term could just keep growing and growing and growing more and more and more. And now maybe if your set point changes where you want to get some other point, it can be very hard because it's sort of wait a long, long time before this integrator builds back down. So all these are kind of nasty effects of integral control. But in general, what's very nice about it is that you are able to track systems and in general trajectories, but certainly track set points like this. That is, achieve a set point from arbitrary starting conditions without actually knowing what feed-forward control you needed to achieve that in the first place. One comment is that in picking these gains here, Ki is a little bit different in terms of its scaling. Because you are adding these up at every time, you kind of want to include something that talks about what the time step actually is, right? Because if you're sampling this 1,000,000 times a second, you would add this up 1,000,000 times, the error here. Whereas if you sample only 1 second, you'll only add it once. So you probably want to include your delta t in Ki itself. So I'm using actually Ki equals 15, but then times delta t. So it's only on the same kind of scale as the other two if you do, in fact, use the same time step. And in general, in continuous time, you actually would replace this with an integral instead of just a sum in the exact continuous time formulation. But again, anytime you actually implement it, you're going to be sampling these are some discrete times. So we'll just sum them up. All right, any questions about this? Yeah?
In the last one, in the parentheses, we did minus.
Yes.
The last one.
Oh, yes. Oh, sorry. Good catch. Now, despite the fact that this seems, because a lot here, a lot of tuning you have to do, right? You have to pick all these different gains. You have 3 different knobs, basically, and you have to tune them all. Really, they think of them as knobs, basically. This one gets you there faster. This one sort of slows you down. This one accounts for steady state error. And in picking those gains, you have to trade off all those things, mainly by just observing the system and seeing what happens and then tuning them accordingly. The interesting thing, in some sense, about this kind of control is that it does really actually work quite well in some cases. You would sort of think, well, okay, I guess it can kind of work when you have a one-dimensional system like this, or really two-dimensional, but one thing you're controlling and one's the other states and velocity of that thing. That kind of makes sense, but when you have systems with lots of states where they're all interdependent, this seems like it might not be as practical here, but the truth is it actually can sometimes work very well. And a lot of real control systems are built upon PID control. Because it's so simple to implement, right? You don't have to worry about what the state everyone else is in. You just look at your own state, start adjusting accordingly, and things do converge. So to emphasize that point, I'm going to give a bigger example of actual multivariate control. The PID we talked about so far is for what's called SISO control. It's single input, single output. And even though there are 2 states of the system, you can think of there's only really one thing we're controlling. It's the voltage angle, and then its voltage angle's velocity, right? But it's really one output in some sense of the system that we want to control, the voltage angle. And in fact, if we do have just a single system that is a linear system with this term, with this thing we're trying to control and its velocity as the state, actually, in a sense I won't really talk about too much, but actually PID control ends up being an optimal method. in particular PD control actually. If there's no steady state error, then PD control actually is an optimal method. And you can pick, what I mean by that is you can pick gains that actually do in effect optimize some cost function. Don't worry about that yet, but that will make a little bit more sense maybe when we talk about true optimal control, but just as an aside. But the tricky part is, what if we have some bigger system like this? Kind of general, c plus 1 equals axt plus b ut. How do we apply a similar type of control here? And in fact, you can only really do it when a and b are of a certain form, but we'll talk about an example now where they are of this form, and even though this matrix A makes all the states kind of depend on each other in a weird way, if you have many generators, for example, the power flow constraints would make all of them interconnected. PID control still can work very well. It does, however, often require a fair amount of tuning. So you have to really be careful with those knobs that you have, and really, it's kind of an art, right, of tuning them to be the right values. All right, so let's talk about a more complex example now. And I'll spend a little bit of time discussing this because it's a little bit complicated, but it really just takes that single generator case and goes to the case of many generators now that are connected by a power grid. So this is exactly those differential algebraic equations we talked about before. But to simplify them, instead of using the full power flow equations, we're going to use those DC power flow equations you've all been having a great time with on the homework, I'm sure. So we're going to use that simplification to make things nicer. All right, so the basic idea is we have these same generator equations, but we have them for each generator in the system now. Right, so the voltage angle of generator I equals, oops, not make a dot, equals the rotational velocity generator I minus the reference velocity. And just as before, the angular velocity at generator I equals 1 over 2h. I'll assume all the generators have the same moment of inertia even. Just keep things simple. This will work just as well when they all have different ones. If you want to say this, they're all different moments of inertia, which is much more realistic, in fact, but I'll just say they all have the same just to keep equations simple. Actually, I wrote 2i, the hi there. I'll write it. Yeah, I guess I'll write it here. I'll keep things consistent between that and the notes. So that they all can have different moments of inertia, different generators, right? They have just different rotors, different weights. They're going to have different moments of inertia. And then the input you put into the ith generator, which is the mechanical power, how hard you're turning that crank, minus P electric at that node. And that's the power that is put on the generator by electrical system. And in fact, to keep things simple, I'll even just, P is always going to be electric power, so I'll just write P. So that's our generator equations. The next set of equations is our power flow equations. And we're going to use the DC power flow approximation. So our whole big vector of powers, that includes powers for both the generators and the loads. Generators are the ones we're deciding here, but the loads are known powers. This equals our susceptance matrix B times theta. Before in the homework, it was actually negative B here. I'll just roll that negative sign into the B. You see both conventions actually in the literature. This one actually looks without the negative sign. It actually looks more like an admittance matrix because you get that negative sign from inverting J. So you see it both ways. I'll just, for simplicity, leave it with the understanding that there actually is sort of a negative sign there if you use the notation we used in the last homework. Yeah?
Are those two P's the same?
Yes, of course. They have to be. And these two thetas are the same, too. This is what relates these things together. This is a set of differential algebraic equations that relates how these variables evolve. I mean, this evolves, and the only reason generator 1 depends on generator 2 is because their powers have to obey this equation. The powers and voltage angles have to obey this equation. Okay, now this is one of these differential algebraic equations, which are sort of nastier. They seem nastier to solve, right? Because you had this set of equality constraints along with differential constraints. You have to kind of typically use Newton's method. But what happens here is that these are linear constraints. And in the case of linear constraints, we can actually simplify this substantially. Usually, not always, but in this case we can, to convert this to a purely differential set of equations. So I'll go through this next few steps here. It's in the notes. It's a little bit tricky if you haven't seen it before, but it's just linear algebra. So I'm going to write it down. If it starts a little bit, if you don't quite follow, don't worry. I'm just going to write down how we convert this whole thing, which has an equality constraint here, into just a pure set of algebraic equations. And to see sort of what's going on here, the problem, right, is that the variables, our state variables, remember we have the differential variables, which include this, so I guess theta I for I being a generator, and omega I for I in a generator. These are our differential variables. And then we have other variables, though, that are determined by these algebraic equations. Namely, we have the power at the node I for I being a generator. And we have the phase angle at the loads. That one is also determined by these equations, but we don't, it's determined by what the powers are themselves. So theta I for I being in the load is the algebraic variables. And then finally, we have some things that we know, right? We know Pi for I in the load. That's assumed that we are given that and we know what the different loads are. So the idea here is this is not a very nice sort of expression, because what we want is we want some way to just replace all these things here, which is an algebraic variable. We want to replace it with what it equals in terms of the things we know. But it doesn't quite give us that, because some things here we know, some things here we know, and it's kind of a little bit nasty. So what we're going to do, it really is just a bunch of linear. It really is just a bunch of linear algebra. But again, it can look kind of hairy if you haven't done this before. So I'm just going to go through it. And again, if this doesn't really make sense, don't worry. You can go back through it through the notes. So I'm going to separate out this equation in terms of those variables that depend on the terms of those nodes that are generators and those nodes that are loads. So I'm going to write it like this. This is the same equation here. I'm just going to write it with the generators and loads being explicit. I'm also going to partition B to also have this form. GL, BLG, BLL times theta for the generators and theta for the loads. Okay? I'm just rewriting that. Next, I'm going to write down the equation for what PL is. Remember, PL is known, so we shouldn't really define it in terms of things that we don't know. We should just write down what it is. And what we don't know, though, is theta L for the loads. So let's write down part of this equation, defining PL here. So PL, just by matrix multiplication, would be equal to BLG times theta G plus BLL times theta L. We know, or these are things that are known. These are differential variables, which we sort of have up here, which we want to convert everything to. So we don't need to do anything with that. These ones are the ones we have to solve for. So let's just invert this whole thing to give us theta L equals BLL inverse times, I'll just write them out all explicitly, but BLL inverse times PL minus BLL inverse times BLG theta G. Okay, so I've just taken part of this equation here and written the solution for these variables in terms of those linear equations. Yeah?
How do you know that BLL is inverse?
So you don't. So the assumption here is that BLL is invertible in order to do this. Otherwise, you actually cannot take us out of the differential algebraic form. BLL, in most cases, though, will be invertible for a thing like this. So I guess I can't really talk about this too much because some people still have their homework out. But what you'll see from the homework, ideally, is that certain subblocks of this B matrix are, in fact, invertible. And in the case, usually L will be for some pretty reasonable assumption. I think they have to just be connected, essentially. Connectedness, this will, in fact, be invertible. Yeah, as long as this whole grid is connected, these will be invertible. And it could be even if they're not connected, but that's a sufficient condition for it being invertible. OK, so now we've got this equation for theta L, which defines our algebraic variables in terms of some of our known and differential variables. Our other variables, algebraic variables, are these p's at the generators. So let's write this out too. So we know that p at the generator equals bgg theta g plus bgl theta l. Let's take our form for L and substitute this back in here. And what we get is that we get bgg. Remember, theta L has a term that runs theta g too, so I'll group terms together. bgg minus, let's see, so this times this guy here times that. So this is bgl bll inverse blg times theta g plus it's this guy here, so plus bgl bll inverse pl. And now this defines our other set of algebraic variables in terms of things that we know, the known quantity here and the other differential variables. And in fact, here, the only variables that appear in this equation is this term here, p for the generators, right? So we're just going to plug this equation into our differential equations here, and we have eliminated all these algebraic variables. So that was kind of fast, but again, you can look through the notes again. All we're doing is we're just plugging this in here, and so what we get in the end is we don't need this anymore because we've described all these constraints. And so instead of pi, though, I was actually writing it kind of for all of these. So sort of like all the vector of those things equals u minus this whole guy here, minus pg, where this pg is defined as this whole guy here, and I'm writing it out here. So these are our new differential equations. Now given in vector form, so this is actually defining what's going to happen for all the different theta angles and all the different omegas. Now what's interesting here is that what happens is that this matrix in general will actually be full. So you have a dependence on omega dot depends on all the other generator voltage angles. So it's not as if each generator operates independently anymore. What you now have is they're all tied together because the actual voltage angle, right? So my voltage angle sort of is affected immediately by my omega here, but my omega here is affected by all the other voltage angles. So these things can kind of quickly become very complex systems, right? Where everything depends on everything else. Yeah?
Yeah, I remember in the homework 3 that P equals to negative B times theta.
Right, so that's what I was saying before, that I'm going to roll that negative sign into B. Those notations are both common. You'll see both. You'll either see P equals negative B. Sometimes people define negative sign in the elements, or sometimes they don't. Okay, yeah.
What's the control goal here?
Right, so let's say the control goal is to get all the voltage angles to some desired quantity. Now, depending on what their quantity is, you'll end up actually producing different amounts of power at each node, right? Because power and voltage angle are still related by this thing, by b theta, right? So in the case of your homework assignment, what you did was you assumed that the powers were all known except for the slack generator, and then you solved for thetas to give you those powers. And so similarly, you could just plug in some thetas here and see what power came out of it, right? So the goal that we're going to talk about here is, and this is not the best goal necessarily, and they're kind of arbitrary too, because oftentimes generators won't actually do this. It's actually even hard sometimes to measure your voltage angle because it depends on some kind of true reference out there somewhere, reference to 0, right? And so you actually need things like that can actually measure phase relative to a global coordinates, relative to a global timing system. So it's not always done this way, I should also emphasize in practice, but the control goal we'll focus on here is maintaining some desired set of voltage angles for all the generators. And that will imply, by the way, they all generate a certain desired amount of power too, right? Because given the loads and given desired voltage angles, I mean, here's how you do it, right? Here's how you compute how much power they all generate. Yeah?
Is there a concept about what's the difference between this BLT and BCT?
So these are just, all it is this is just a sub-blocks of this matrix here. So this is just that susceptance matrix, which is like the admittance matrix with just reactances involved, no resistances. And so all this is I'm just partitioning this matrix for the elements that connect the generators, the elements that connect generators to the loads, and the elements that connect the loads to the other loads. So it's just sort of the B matrix, but it's just the B matrix chopped up into partitions that talk about generators to generators, generators to loads, and then loads to loads. Yeah? Mm-hmm.
Can you do this for AC?
No, you can't, because in that case, you can't directly invert these equations. That's the whole problem with AC power flow, right? You need to use Newton's method to solve this. What you do in practice is you actually do something very similar to this, but you plug in the Jacobian here as a linearized version of this constraint. But you have to repeat this process then like Newton's method, right? So you can't do it directly. The reason why you can do it here is because this is a linear set of equations, you actually can invert it analytically. All right, so now we have a system. Again, our goal is going to be to, and I guess I don't even quite say it here, but our goal will be to achieve theta for the generators, I guess, equals theta generators desired. So we just have some voltage angles that we want to obtain. Let's say we can actually measure them all too in a single system, which is not trivial, right? Again, because these are far apart and you have to know exactly how this guy's rotating relative to this guy over here. That can be tricky. But let's say that we know this. We can at least determine what these things are. And we just want to achieve some desired ones. That's our goal. So, things seem a lot harder here, right? Because they're all interconnected. Do this term here. Everything's connected to each other. But what we could do is we can ignore that entirely. Right? Let's ignore that. Let's just set ut equal to, let's use PID control to control R, and I guess it really should be UTI, right? Because we're going to set the ith element as if we were just operating independently, as if there was no one else around, and we just could set it whatever we wanted. Again, this is sort of trickier now because we really need that integral term because we don't necessarily know what P elect is going to be. It's determined by everything else moving, so we reasonably need integral control here. And let's just set it as if we knew what all the variables we needed, right? Let's set it to be equal to some kp times theta t I minus theta d. Sorry, it's the other way around. Take the desired ith element of theta minus whatever r element of theta actually is. Let's also slow it down. I won't even write the desired. We'll just assume desired is 0. So we subtract negative k d times theta t dot I, and then plus ki times the sum of tau equals 1 to t theta id minus theta tau I. I think that's right. The signs are right there. Okay, so this is exactly what we saw before. And we're just completely ignoring the fact that all our things are coupled on what everyone else is doing. All right? So this, I mean, it's almost kind of surprising if this would work, right? Because there's all these effects that are out there that we're just ignoring. We're just saying, I don't care. You know, in theory then, you'd want to take control actions that depend not only on your state, but on other states too. You probably want to adjust your controls based on how close everyone else is to their desired state, right? That's what you should do in theory. And we're just ignoring that entirely. And we're just saying, I'm just going to look at my own state, take actions as if no one else was around. And the really crazy thing is this actually can work pretty well sometimes. So here's what happens with this. So here are all the generators. I'm starting off at some sort of arbitrary angles here. I'm showing theta minus theta d here. So this shows for each generator how far it is from its desired amount. One actually starts at it. The slack generator actually starts at its desired amount. They all, I guess they all start at voltage angle 0 in the simulation here. And they all have different desired voltage angles. So other than this blue guy, which starts at 0 and wants to be 0, they all started with some error. And they kind of take some interesting trips through the space here, where they kind of swing back and forth. And by adjusting gains again, you can make this swing back and forth less and converge more smoothly. But what's amazing is that it actually works. That operating everything independently, you actually do in fact converge to the to the sort of global thing you're trying to track. So this is why, by the way, PID control is so frequently used. It's because it does work, even when things seem really complex. Yeah?
So here you design each generator PID control.
So I'm just actually doing the exact same gains for all of them. Same gains. They even have different moments of inertia, each of them. So you probably wouldn't even want the same gains. You'd want different gains. And you could assign different gains if you wanted to. I'm just saying assign all the same gains, and it works. And what you're essentially doing is that PID control is, it's good at kind of rejecting a little bit of disturbances, right? Because if you start a little bit far away from your system and there's some disturbance that you didn't model maybe, it's kind of good at correcting for that. And what's going on here is that the effects of all other generators are being treated as a disturbance effectively. So you're saying what everyone else is doing, it's something, I know it's going to affect me, but I'm just going to treat it as a disturbance, and I'm going to just operate as I would anyway. And here, like not always, but here, it works. So this is one of those amazing things that sometimes these actually can work really well, even when the system is really nasty. Yeah?
So what's the difference of these generators? Like only the initial value of the theta minus theta d?
So the theta d is different for all of them. You actually want, so they all start at the same actually initial theta. They all start at theta equals 0, and theta d is what's different for all of them. The other thing that's different is they all do have different moments of inertia. This is not great for a multivariate equation. Then it would be like the diag of this thing, right? But they all have different moments of inertia, and they all have different desired angles they're trying to achieve, which is not the same as their initial values. Yeah?
So you just solved for PID earlier.
Yep.
But then why wouldn't you just use that in your U of T?
P of G tells you what the power generators are right now, given the other factors. It's not what their desired power should be. It tells you, given all your other states, namely the voltage angles here and the voltage angles of the generators and the power of the loads, this tells you what the power of the generator actually is. And that is not their desired values, right? Because that is different depending on what these guys actually are. So and when you start off, this is something different from what this converges to. PG there. Now you can, invert, just take your original power flow equations and determine what your power should be for all the generators and use that as a feed-forward term. And in fact, you can do that. That requires that you actually know this whole model. What's amazing here is that you don't even need to know the models of any other generator other than yours, right? There's nothing in this control law that talks about what anyone else is doing. What if they don't, follow their rules and they don't quite achieve what, they don't output the power you think they're going to output? Well, you will still maybe put a little more power in, but you'll still achieve your voltage angle that you want to. Again, achieving a voltage angle is somewhat of an arbitrary goal. You don't really control to do that usually in real power systems, but it reinforces the fact that PID control for that task can work very well, even when things are not coordinated.
So why do we even need to solve for PG?
This gives us the actual dynamics of the system. So to simulate it, I have to actually have equations for what's going on, right? If I don't have equations for what's going on, I can't run anything. I'm just describing the dynamical system and then showing that it is correlated, so there is its dependence. That's the true system here. I am prescribing control line now that does not depend on that sort of true system, and lo and behold, it works pretty well. So that's almost really surprising that it does work so well. And it doesn't always work, but it does work sometimes. And this is really why PID control is so commonly used, is because you can sometimes work with very little effort. If you wanted to design the right controller, which we're going to do in a second, you have to really know the state of everyone else and everyone else's, the true set of equations that you are simulating here. That's all required to develop really the optimal approach to control. But PID works really well. And I guess depending on your perspective, this could mean that, let's just do PID with everything. It could also mean, well, PID is really hard to tune, so let's not. Let's just measure the other things and actually try to do better. But these are trade-offs you come across in control.
Have they compared using PID versus?
Well, optimal control by definition will do better on whatever you're optimizing. It is the optimal control for that. So it's much more of a comparison about effort involved and kind of these more harder to quantify variables. Are the real trade-offs here? Yeah.
Can you actually analytically specify when PID works?
Yes, you can. I haven't really talked about that yet. To know when it works, you really have to look at stability of systems. So remember, I talked a little bit about stability, right, in terms of the eigenvalues of this matrix. What you can do is you can actually formulate PID control as another linear system. You can, the system with that controller becomes a bigger linear system. It's actually pretty easy for PD control. It's not that easy for PID control. You can do it, so you have to add an extra variable that never converges because your integrator does not converge to 0 necessarily. So you have basically one eigenvalue that's on the unit circle that's unstable, that corresponds to your integrator, and then everything else is inside the unit circle, which corresponds to stable eigenvalues. And that's how you analyze these things. And yes, you can show that analytically, when you plug this controller into the full system, it will in fact converge for any value. In any initial state, it will in fact converge.
Is that another linear system called something like Laplace domain?
No, it's different from the Laplace domain. Laplace domain is actually looking at a sort of set of polynomial equations that can also describe this system. It's better to think about it in terms of the actual eigenvalues of this combined system, right? So you can write. So forget about the integrator for now. I'll talk about this actually in a second when we talk about the connection between linear quadratic control and other things. But essentially, you can think of PD control as setting U. So PD. So say there's U equals some feed-forward term plus some matrix K times xt minus x star. Right, so you sort of look at how close you are to the desired point, you add some constant term of that, and then you multiply this. Since x has both the, remember x, the state has both the thing you're trying to control and its derivative, so you have both the terms there, and so you can then look at the system a plus bk, and look at these eigenvalues, and that determines whether these things are stable or not. Don't worry about that if that was going off on a tangent there. We're actually going to talk about that in a second now, so hopefully it'll make a little bit more sense right now. All right, so now let's talk. Let's go back now to this optimal control framework. Remember, one of the tricky things of PID control was that it often is hard to know what you're really doing by tuning those gains. And there has been a huge amount of work really on gain tuning as in terms of the effect it has on the actual observed system. So these effects like this, how much overshoot is there? How quickly will that settle? What's the frequency of those oscillations? There's been a huge amount of work on understanding how gains directly affect that. Well, let's take a little bit of a different approach here, and let's go back to our setting of optimal control. Right, and let's say, look, let's stop thinking about gains, about just prescribing controller, because it can be hard to say what you want out of a controller, right? What do you want out of those, or rather, it can be hard to say sort of what you want out of those particular numbers that are the gains. What's oftentimes much easier to talk about is what you actually want out of the state and controls you see, right? So this is the optimal control framework, right, where we don't really care about, we don't want to have to tell the system what to do in every case. What we want to do is define some cost function, which is the sum over some time horizon h of the cost of the current state, the current control. And we want to pick controls that will minimize this. And just intuitively, it really is the case that it oftentimes seems more intuitive to define what we want out of a system in terms of costs. Don't be too far from where you want to be. Don't apply too much control actions. It can be much easier to prescribe what we want out of a system in terms of these cost functions. And this is the optimal control paradigm, right? We tell it a cost, and we say find the controller that minimizes that cost. And remember, when, for the intro, we talked about, when the dynamics of a system are linear, and we put, we use a convex cost, and maybe we also put convex constraints on what the states can do, we actually can solve this with optimization, right? That's what we saw in those first lectures. What's also interesting, though, is a very particular case of this. And this particular case really makes clear the connections between PID control and this optimal control framework. And this is called, in general, this is broadly called linear quadratic control. The idea is, so we have a linear system, xt plus 1 plus a xt plus b ut. Linear system. You can do the same thing for an affine system and other things, but we'll just say linear for now. And importantly, your cost function is a quadratic function of the states and controls. So cost xt ut equals some essentially some norm terms. Q xt squared, so we multiply xt by some matrix q. That could just be the identity in the simplest case, right? We want all the states equally to be independently equal to 0. So we get a cost for having them away from 0, and say the cost is a quadratic term. And we do the same thing for the controls, because we also don't want to apply arbitrarily large controls to get what we want. And we saw in terms of the discussion on controllability and observability that you could achieve any state you wanted if you just allow your controls to be crazy enough, or for a controllable system at least, you can do that. You can't do it for every system, importantly, but for a controllable system, and from now on, we're really going to talk almost entirely about controllable systems. If you can't control them, they're kind of hard to talk about control in uncontrollable systems. But for a controllable system, we still probably want to put some kind of penalty on our choice of actions too, right? Otherwise, we're just going to take these huge actions that'll get us to a good state, but we aren't. This isn't really helpful if those are completely unrealistic in practice. And this framework as a whole is called the linear quadratic regulator. Also referred to as LQR. And it's really one of kind of the workhorses of a lot of control methods, a lot of sort of practical optimal control. Linear quadratic, linear because the state is linear, quadratic because the cost is quadratic, and a regulator because the cost is equal to 0 if and only if both the control and state are 0. So if, and by the way, because the system is linear, if you have state 0 and control 0, you will stay in the 0 state. So you want to regulate the system around this state of 0 control and 0 input. Now, for cases where this is not the case, where if you put 0 input in, you will not go to the next. You will not remain in the 0 state. What's common is to actually formulate this problem in terms of differences from the optimal state. So suppose you have some affine. Actually, you know what? I talk about this in a little bit, so maybe I'll wait till I do it. But basically, if you have something like an affine system where you don't get 0 next state from 0 control and 0 input, you can actually still do this thing around an equilibrium point in the system, where you set up a new system where states correspond to differences between your desired state and your actual state. And we'll see that in the next few slides. So I just want to emphasize here that this can apply to cases also where you're trying to achieve some state that is not equal to 0, but you have to just play a few little tricks with the math then that aren't very hard. So this is the LQR framework, and it's hugely, hugely used in practice. Remember, we can write this as an optimization problem. So we can formulate this whole thing as, we want to minimize over some time, I need to write this. We want to minimize over some time horizon the sum of our costs, which in this case is the sum of these different norm terms, subject to the constraint that xt plus 1 equals a xt plus b ut. So even though x1, I guess I should also have written that x1 equals some fixed state here, right? So we have these constraints and also the fact that x1 has to be defined. Otherwise, it's not very good to have it as a variable. So essentially, even though the x's here are all variables, they're really being constrained by these equations here, so we can't really choose them. I'm just writing it this way because this is sort of our formulation for optimal control, and it's convenient in a lot of cases to actually do this. What's very interesting about this case, and here's where I'm going to be completely hand-wavy and not actually describe what's happening here. What's very interesting about the LQR case is that the optimal control, so the solution of this optimization problem, takes on a very interesting form. It takes on the form that ut equals some matrix kt times xt. This is now a matrix. Kt is a matrix. It's going to be a m by n matrix because it multiplies an n-dimensional state and returns an m-dimensional control. It's not that hard to prove this, but it does take a few lines of linear algebra. And the point I want to make is just the fact that this does hold. If people are really upset about that, I'm happy to go through it, but you have to do a few lines of things like dynamic programming to describe why this is in fact the case. Yeah?
In this LQR framework, for according to the objective function, you don't care about keeping the theta angles constant.
So the way you would apply this framework, which we'll see in a second, the application of this to that task. What you would say is actually you would define a new state, delta xt, which equals essentially theta minus desired theta, and then omega minus omega ref. So you would actually define a new state equal to that. And that you do want to keep 0, right? Because that would mean being 0, that would mean that you're at your desired angles and you're there. Now, this cost function applied to that delta x would capture the fact that you want to have these be equal there, right? Because you're just taking the norm of this thing and just say we don't multiply by anything, we just take the norm like this. That's going to be 0 only if these things are all equal. Only if this thing is 0, so they're all equal. So that's how you capture criterion like I want to be at a certain state, or I want my voltage angles to be at certain values. And what you see is you'll get a very similar form here. You'd say that delta ut, which would be sort of the difference between ut and the best and sort of the equilibrium control, would be equal to submatrix k times delta xt. We'll go through that in a second, how that pops out exactly. The point, though, is that you do get this very nice form for the solution. Now, what's even cooler about this case is that we can even go beyond what I was talking about before and think about an infinite time horizon problem. So let's minimize this cost function not only over some finite horizon here, but actually over an infinite amount of time. So it may seem that seems weird, right? Of course, in this class we deal with infinite stuff all the time, and it's no problem. But you know, how do we minimize? You would think, you know, you could just wait a while and get to its state later. How do we minimize this cost over an infinite time horizon? Or could then that actually be infinite itself, right? Couldn't the cost, therefore, if you're looking over an infinite amount of time, wouldn't the cost also be infinite, perhaps? What saves us here is the fact that we know there exist actions that will have finite cost, right? Because we know the system's if the system is controllable, which we're assuming throughout this system is controllable, then we know we can find some sequence of u's that will make the state equal to 0. Right? From then on, the state is going to be 0, the control will be 0, because this will hold here. And so we know that for that sequence of states, of controls rather, this whole thing is going to be finite. Right? Because it'll have some costs for some, up to some k steps, and then it'll be 0 from then on. Because of that, it actually is the case that the minimum over all possible controls will also have finite cost. I guess I wrote t's here, so I should have written infinities there. So we know that there exists some solution to this problem, basically because we know there exists some point with finite cost. So there has to, you know, we can just do better, or we'll just optimize a little bit more. And what's very interesting is that this solution actually takes almost the exact same form as LQR in the finite time horizon as I told you about before, but it's actually even simpler. The optimal action to take, given an infinitely long horizon, is always given by ut equals some fixed matrix k, that's not dependent on time anymore, times xt. This is even a little trickier to prove, that this always exists, in fact, when the system is controllable. It's more linear algebra, but this to show that it actually converges a little bit even one step beyond that. If anyone's curious, I can point out some references there, or I can chat about it more, but it's not that easy to show. Not that hard either, but I wouldn't want to write it in you know, half of a class or 10 minutes, whatever. the 10 minutes we have left, I wouldn't want to prove it in that time. But in fact, and again, as I said, the intuition here is that if we can achieve it with some set of controls, we know that this cost has to be finite for some u. Therefore, it has to also be finite for the optimal u, right? There has to exist some u that is good. And in fact, this is the optimal. There exists some k where this in fact, that k gives the optimal set of controls. The k is nasty what it actually is. It depends on some recursive equation. You have to find a steady state to a recursive equation and then compute some function of that recursive equation. But lucky for us, there's actually just a command in MATLAB that'll do it. You just type in DLQR, put in AB, Q transpose Q, and R transpose R, and that'll work. That gives you K. Actually, it gives you, by their convention, it's actually negative K. They have a negative there, so you should actually put K equals negative DLQR. And if you want to see what function is actually solving, you can just do the help on this guy, and you'll see. I probably would make a typo if I actually tried to remember it. I think I could probably write it, but I'd probably have a typo somewhere. Okay, so again, this is kind of all very hand-wavy because I don't want to get into the actual definition of this. We're going to really focus mainly, much more in this class, on just those optimization problems. So we're really just going to go back to this thing, not the infinite time, but just the finite time horizon case. And we're just going to solve them with a convex solver. The added benefit there, which is very important, is you can actually add constraints on these things. This is unconstrained, which raises some major problems. But the reason for this is very good at making connections between this and PID control. And so it's very valuable to see those connections and see how they relate to each other. And LQR is a really good way of seeing that because it is an optimal control method that gives you a form of control very similar to PID control. So let's see why it's actually similar to PID control. Maybe we actually get through all of these in the time we have. So take our generator example. This is our set of equations for the generator. We can write this as a set of linear equations. I'm going to write it in terms of its derivatives right now, but I'll discretize those in a second. So x, again, is our vector of all the voltage angles, all the rotational velocities. A is this big thing, right? Because A, the derivative of the voltage angles depends just on the velocities. And then the derivative of the angular velocities depends on immediately and just on the phase angles, voltage angles. And then we can put an additional power to affect what the time derivative of the rotational velocities are. And then we also add some extra term, which corresponds to the fact that we have this extra constant term here and here. So you can just verify that these are, in fact, a set of linear equations that represent this exact same thing. OK, now let's go ahead and put this into discrete time. So what we get is we want to put it in with some time step t, just by Euler integration, the simplest case. We'll just take the identity plus delta ta xt plus delta tb x. Sorry, delta tb, that should be a u. I have it written there too, but sorry about that. That should be a ut. And so we can convert this to a affine discrete time set of equations. Now we're going to do this trick I was talking about before, where we're going to represent these equations in terms of differences from the state. Do I have time to do this? I don't want to skimp on this time. We'll see. Maybe I'll have to finish this up. We have such a long break afterwards that I'm sort of hesitant to do it. But I did want to say a couple more things. So here, maybe I'll give a broad outline of what we're going to do here. And then we'll go through it in more detail next class, so a week from next Tuesday. So it's a long time before we have class again. What we're going to do is we're going to define a different linear system in terms of these deltas here, right? Where delta t is equal to xt minus some equilibrium state. This is actually the desired voltage angles and the desired reference velocity. We can show that actually this equation here with the affine term is equal to this thing here, as long as we pick x star and u star to obey some equilibrium condition. So we can transform this into this same A and B matrix here, just with delta t's instead of UT's. Now we run LQR with some costs on the differences. So that's what we want, right? Because we want to penalize how far we are away from the desired state and how far we are away from maybe the steady state control. And what we get is we get a optimal controller that would say that, well, delta UT is equal to K times delta XT. And all this means is that UT equals some, just rearranging terms here. This would just say that UT equals our optimal feed-forward term plus K times this difference here. Now, again, going through it in more detail next time, what we'll see is that this is the LQR solution, right? The PD solution is this exact same form. Again, this is PD with sort of the right feed-forward term. It's also, you apply kind of what you would apply if everything's going well, plus some other matrix of gains times this thing, where these are the KP and KD gains here. And you can verify these are, in fact, with this definition of XT, remember here, this is, in fact, the exact same thing as the PID control. Right, so this is the exact same form. It's some matrix times the difference in our states. The only difference is this K matrix we get from LQR is typically a full matrix. In other words, it'll use the fact that states are dependent on each other to actually adjust your control depending on not only your state, but on everyone else's state as well. And in doing so, it will actually achieve a better objective than PID, or just here PD will. The value of LQR, though, is that by just specifying some cost, we don't have to think about kind of these cross terms and the gains. We probably don't care that much about sort of, how should this state affect how we control this other state. I mean, that's very unintuitive, right? The nice thing about LQR is you can just define costs. And in fact, even just ignore this Q. Let's just make the cost the actual norm of these two things, right? So we want to penalize deviations from the desired theta angles, and we want to penalize, maybe how much extra power we use. That's a very intuitive description of what we want to optimize. And what LQR does is that given that description, it will output a set of gains that are the best ones possible for achieving that in this infinite time horizon setting. There's one question back there.
Yeah,
quickly.
So you're saying that the LQR control inside is actually PD control?
It's not PD as I defined it, because I was defining PID in terms of you only take an action based on the error in your own state. So each generator only changes itself based on sort of what its own state, how its own state is diverging from the global state. If you define PD controller in terms of you can take an action based on what any one state is relative to anyone else, then yes, LQR gives you that type of controller. But I think that the point of LQR is that it's giving you a controller of the exact same form, again, modulo the fact that the PD control I showed only has diagonal terms here.
I mean, so inside MATLAB, so they are designed this algorithm as the form you provided, or you are just finding that they are in the same form?
They provide it in this exact form, but K is going to be a full matrix, yeah, and when states are independent. So it sort of depends on what you call PD control, right? The algorithm outputs this exact form.
Yeah, in normal, just treat Q as a weight of state and R as a weight of control. So we didn't look into that much.
Right. So the point, though, is that you get something that's exactly the same kind of form as this. That's sort of the idea from this. Yeah, and it can be much more intuitive to represent kind of just the cost in terms of just weighting on your different states. Say these are diagonal, and so you just weight the states differently. That's much more intuitive than trying to actually come up with a element by element full K matrix. That would be nearly impossible. Maybe the diagonal ones are okay, because you can kind of think about what that might be. This would be really hard. So this is the benefit of LQRs. It will give you the optimal controller for those costs in a form much like a PD controller. It's a set of gains that sort of say, you're different from your desired state. Here's how you should adjust your control. But it does it in a way that's sort of very intuitive to specify for a designer of a system. I will go through all this again next Tuesday, because I went through it pretty fast right now. We'll see it again. And I may also put some examples showing what LQR looks like, in fact. But that is the benefit of LQR. And also, the bigger point is that it kind of does show there are connections now between this PD control, where you're just picking gains. It seems like there's something optimal control about it, and real optimal control where you are designing a cost function and minimizing that cost function. Okay, so now we don't have class for a while, and I'm running about a little bit of time, but I want to just mention a couple of things. Again, we're not going to have class next week. We have class the Tuesday after Thanksgiving break, is the next one. The other thing is the homework. I mentioned this when I got here to class. Given the last homework, I actually wanted to make a few changes to this next one to make it a little bit more explicit some of the problems and walk you through step by step of what you do. I think as it was initially, it was a little bit too, maybe the last homework also, and this next one was going to be as well, a little bit too open-ended, and some of the things were only implied, not said. So I'm redoing some of it to make a lot of the problems more explicit. Having said that, this next problem set essentially walks you through one single problem of designing an optimal controller for scheduling, generation, and storage in a smart grid using machine learning forecasts of things like renewables. So we're really bringing together everything we've done so far in this class all into one system, and we're respecting things like the power grid and all those constraints. So it's almost a research level kind of project. So do start early on it, especially the first problem or second problem you should be able to do pretty right away. Maybe the third problem we won't quite get to yet, but should lead into it pretty easily. But do take a look at it over break or sometime, just sort of see what's going on. It's also a lot of text, because I'm writing out a lot of stuff to describe kind of how to go through it step by step. And this is actually a change from the original assignment. So some things that were going to be problems are no longer problems, but it's really focusing on one big sort of sequence of things you should work on. And I think that was all I'm going to say about that. So was there any, and that will be out, right, when it's going to be out. I'm going, changes maybe delayed a little bit, but I'm going to have that out today or tomorrow, and the latest on Saturday. So it's not, you have 3 weeks to do it. So do it, but do also start looking at it as soon as you can, because some of the problems you can start right away, you could do right away. We've covered all the stuff, and it will be of the form like the last homework, where later problems build on earlier problems. So you really want to get those worked out before too long, so you don't have to do it all at one time. Okay, well, I will see you all after break. Have a good Thanksgiving.
Yes.